Last time we began to talk about the different types of ensembles that we'll deal with in statistical mechanics. One of the more common examples that one of the more common ensembles that we'll use is the canonical ensemble. We're doing a I'm going to warn you ahead of time, this is a very formalized definition of the ensemble. We will put it in much more practical terms later on when we use it. So we had stated that the probability distribution in the canonical ensemble would look like this, where theta and psi are independent of Q and P, but they're what we call distribution parameters. Let's talk a little bit about that. I can write my, again, my number of ensembles in this way. By doing so, I can solve this equation in terms of this exponential e to the minus psi over theta. And the reason we do this is to kind of get a better idea of what psi and theta might be. We're not going to say right off. We're just going to leave you with this idea, but here's what we want to do. The bottom line in canonical ensembles is that nearly all of the systems in the ensemble have energies that are very, very close to the average ensemble energy. And the reason that we know this is, well, for one reason, for systems that have many, many degrees of freedom, the volume and phase space increases very rapidly as regions of higher and higher energy are included. This is going to depress the number of systems that have less than average energy. But on the other hand, the distribution law tends to depress systems that have greater than average energy. And if you put those two together, you're going to have a very, very high concentration of systems that are right at about the average energy for the system, for the collection of ensembles. Collection of systems in the ensemble. What that means is that we can very well use the canonical ensemble for systems where we know the average energy. That will also lead to ideas about knowing the average temperature, but that's going to come later because we really haven't defined temperature yet. So we're going to hold off on that. This will lead us to one of the most important ideas. We may have mentioned this earlier, but I'm going to state it definitively. And this is called the fundamental postulate of equal a priori probabilities. Formal definition says the phase point for a given system is as likely to be in one region of phase space as another. Assuming all regions are the same size. Sounds rather esoteric, but what it's really saying is this. A system is likely to be in any one of its accessible states. Now this is called a postulate, so we can't prove it, but we've never seen an exception to the postulate, and it's extremely useful. So, how are we going to use this? Remember the basic procedure. We start with a system where we have some but not complete knowledge. And we seek to configure a representative ensemble. But to be able to do this, you have to be able to invoke this postulate, because if I can't assume that this is true, then nothing about taking the average of an ensemble is going to be accurate, or at least you can't prove it. So, we don't have a reason to assume that the postulate would not hold in all cases. Practical example, non-physics example. If I roll a pair of dice, I have to assume that any of the outcomes is as probable as any of the others. I'm assuming that the dice are not loaded, that I can get, it's just a chance phenomenon, whatever comes up, whether it's a 2 or a 12 or whatever the number may be. And we should see the occurrence as many times as is probable for a particular outcome to occur. So for example, just take one die. If I roll, any one of the outcomes should happen about 1/6 of the time, assuming I roll the die enough times. Now, there can be some fluctuations with this, but we expect that the fluctuations will be small. This also goes to an even greater level, because when I assume that this postulate is true, I'm also able to determine or predict what outcomes are statistically likely versus what outcomes are mechanically not possible. What we want to do now is let's get down to determining how we can characterize states of a system in statistical mechanics. Oftentimes, we use quantum mechanics because it's a more complete way to describe a system, particularly in the realm of the very small. And we use the wave function psi, which is a function typically of our spatial coordinates, to describe the system. Again, if we had f degrees of freedom, psi would be a function of all f of those position variables. Now, psi itself is an amplitude. It doesn't represent a measurable quantity, but psi star psi or psi squared represent a probability. So in quantum mechanics, this becomes sort of a natural occurrence. Typically, though, what we find ourselves doing is that we operate in classical mechanics because it happens to suffice for a lot of the systems of interest. Let's talk about how we might specify the state of a system. Let's start with a quantum mechanical example. And that is, let's talk about a one-particle system. So this is very simple. A one-particle system. We have it fixed in position, but let's give it a spin of 1/2. Okay? And we specify the spin with respect to some z-axis, let us say. So the spin can be either parallel to the z-axis, or it can be anti-parallel to the z-axis. If it's parallel, we call it spin 1/2. If it's anti-parallel, we call it spin -1/2. Such that when I'm specifying the system, we say that this one particle system has two states. It can either be +1/2 or -1/2 in terms of spin. Since we're not worried about position, that is the only specification that we need for this system. Again, very, very simple. Take another example. Suppose I have n spin 1/2 particles. So now instead of 1, I have n of them. N may be a very, very large number. Again, they're fixed in position, and so the only thing that we are concerned about is whether m is 1/2 or minus 1/2. Is it spin up? Is it along the axis? Or is it opposed to the axis? If I want to describe the state of the system, I would have to know the spins of all n particles. So it's a more complicated case than the first case, but still, we only have essentially 2 degrees of, or 1 degree of freedom. Another very common example that we'll encounter a great deal in statistical mechanics and quantum mechanics is that of the simple harmonic oscillator. So we can discuss, in the case of quantum mechanics, we know that the energy eigenvalues for the simple harmonic oscillator can be written as n plus 1/2 h bar omega, where omega is the frequency of oscillation, n is some integer or 0, and can be 0, 1, 2, 3. What this tells us, you might remember, is that it gives us a 0-point energy. Even if n is 0, there is still some ground state energy associated with that oscillator. So we would describe the state of the system in terms of the total energy, and that would be equal to n plus 1/2 h bar omega. Take it a step further. Another example would be to say, suppose I have n weakly interacting one-dimensional harmonic oscillators. In that case, we would specify the system by not just one n, but there would be n of those quantum numbers to fully describe the system of harmonic oscillators. Another nice example. Take another example from quantum mechanics. Let's talk about the particle in the box. You studied this in modern physics. Particle in a box is, let's say that we have a one-dimensional box. No, we can do a three-dimensional. Let's do a three-dimensional box where the particle is confined to reside between 0 and Lx, 0 and Ly, 0 and Lz. Let's assume there are no forces on the particle. There's a wave function that describes the state of the system, and it's obtained by solving the Schrödinger equation in 3 dimensions. And solving for the energy eigenvalues. When I solve this equation in quantum mechanics, I separate variables and I find the solution is a product of signs. So it's the sine of pi n sub x times x over L, sine pi n sub y times y over L, sine pi n sub z over L. And the energy eigenvalues, you might remember, are h bar squared pi squared over 2m, mass of the particle, and x squared over L squared plus ny squared over L squared plus nz squared over L squared. Assuming that each length is the same, we could or do it in terms of Lx, Ly, and Lz if you like to make a more general case. So we specify this system by specifying the quantum numbers nx, ny, and nz. So before you can even configure an ensemble, you have to specify how we're going to, what items need to be known to configure that system. It's what we call specifying the state of the system. So let's talk about how we might use the ensemble now to describe the system of interest. So, suppose we have a system that has 3 fixed particles, each having spin 1/2, which means it could be 1/2 or minus 1/2, because it could be spin up or spin down with respect to a magnet. That being the case, if we place this system in a magnetic field, let's call that magnetic field H. Let's call it B. We're more used to B as our magnetic field. We can have the following situations. So let's make a little table of what might happen. We'll assign a state number. We'll assign a quantum number. We'll assign a magnetic moment, a total magnetic moment, and a total energy. So I might remind you, for a magnetic moment, if the spin is up, so for spin 1/2, the magnetic moment is what we will call mu. If the spin is minus 1/2, the magnetic moment is minus mu. So let's look at what are all the possible states of this system. So we'll call state 1 is the case where all the spins are up. That gives us a magnetic moment of mu plus mu plus mu, or 3 mu. Total energy, energy for potential is minus mu dot B. So they either point with B or against B. So that can be either plus mu B if it's spin down, or minus mu B if it's spin up. That means in this case, I would have a minus 3 mu times B when I have 3 pointing up. On the other hand, I could talk about state 2, state 3, and state 4, where I have 2 pointing up and 1 pointing down. That gives me a total magnetic moment of mu and an energy in each case of minus mu times B. States 5, 6, and 7, I might have 2 negatives, 2 pointing down, 1 pointing up. That gives me a total magnetic moment of minus mu and a total energy of plus mu B. And the 8th possibility is a case where I have all pointing down. That gives me minus 3 mu as my magnetic moment, and my energy would be a plus 3 mu B. This is the ensemble. So if I have 3 fixed particles, I can describe every possibility by these 8 different states. That's how I specify the state of the system. It's equally likely that the system will be in any one of these possible 8 states. Moreover, according to Liouville's theorem, if the particles are in equilibrium uniformly over their accessible states, they're going to stay that way forever. That's the idea. The probability density will not change over time if a system is in statistical equilibrium. One other thing I'd like to point out before we end this segment is someone might ask the question, well, if I'm talking about a system in equilibrium, how long does it take that system to reach equilibrium? So for example, good example of this, suppose I have a box that's got gas particles on one side and has a membrane on the other. So I've got this nice partition, nothing, so I have a vacuum on the right side of the box, I got particles on the left side of the box. And the question becomes, suppose I remove the partition. At that very instant that I remove the partition, all the particles are still on the left side of that larger box. They haven't had time to move yet. And so the question might become, how long will it take for the particles to occupy the entire box? The answer to the question is, we really haven't and really can't at this time discuss how long it takes a system to reach equilibrium. We only know that it's ultimately going to take place. And of course, that's the point at which we can begin our analysis. Things get far more interesting when we can allow two systems to interact with one another. And that will be the topic of the next lecture.